Subscribe so you don't miss out on any of these videos. The Big Bang Theory is the prevailing cosmological model that explains the origin of the universe. It proposes that the universe began as an incredibly hot, dense point roughly 13.8 billion years ago. This singularity marked the beginning of time, space, and all matter as we know it. The Big Bang is not an explosion in space, but rather an expansion of space itself. Before the Big Bang, the concepts of time and space as we understand them didn't exist, making it a profound mystery about what caused the universe to emerge from such a singularity. One of the most compelling aspects of the Big Bang is its ability to explain the observable universe's expansion. Edwin Hubble's discovery in the 1920s, showing that galaxies are moving away from each other, gave the first solid evidence supporting this model. By measuring the redshift of light from distant galaxies, Hubble demonstrated that the universe is expanding, meaning that in the past, everything must have been much closer together. This realization led to the development of the Big Bang model, which explains the origin of the universe from an initial state of high temperature and density. The earliest moments of the Big Bang are some of the most mysterious. The first fraction of a second, known as the Planck epoch, is a realm of physics we still cannot fully describe. In this era, all the fundamental forces, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, were united as a single force. We don't yet have a quantum theory of gravity, so our understanding of what happened during this period is speculative. However, as the universe expanded, these forces began to separate in a process known as symmetry breaking. Gravity split off first, followed by the other fundamental forces, leading to the universe's current structure. Immediately after the Planck epoch, the universe underwent a period of rapid inflation. This theory, proposed by physicist Alan Guth in 1980, suggests that the universe expanded exponentially in an incredibly short time, growing from subatomic scales to macroscopic sizes in less than a trillionth of a second. Inflation solves several key problems in cosmology, such as why the universe appears so homogeneous and isotropic, meaning it looks the same in all directions. Without inflation, we would expect the universe to have vastly different temperatures and densities in different regions. Inflation also predicts the formation of quantum fluctuations, tiny irregularities that eventually grew into the galaxies and large-scale structures we see today. As inflation ended, the universe transitioned into a hot, dense state known as the quark-gluon plasma, a sea of fundamental particles. During this period, known as the quark epoch, the universe was so hot that quarks, the building blocks of protons and neutrons, could not form stable structures. Over time, as the universe cooled, quarks combined to form protons and neutrons during a process called baryogenesis, which also accounts for the matter-antimatter asymmetry in the universe. This asymmetry is a significant mystery because, according to theory, the Big Bang should have produced equal amounts of matter and antimatter, which would have annihilated each other, leaving only radiation behind. Yet, the universe is filled with matter, while antimatter is scarce. How this imbalance occurred is still one of the major unanswered questions in cosmology. Around 380,000 years after the Big Bang, the universe had cooled enough for protons and electrons to combine and form neutral hydrogen atoms. This period, known as recombination, allowed photons, particles of light, to travel freely through space, giving rise to the cosmic microwave background (CMB) radiation. Discovered in 1965 by Arno Penzias and Robert Wilson, the CMB is a faint afterglow of the Big Bang, providing a snapshot of the universe when it was only 380,000 years old. The CMB is one of the most important pieces of evidence for the Big Bang theory, as it offers a direct view of the early universe. The cosmic microwave background also holds clues about the universe's geometry and fate. Detailed measurements of the CMB by satellites such as the Cosmic Background Explorer, (COBE), the Wilkinson Microwave Anisotropy Probe, (WMAP), and the Planck satellite have shown that the universe is flat, meaning that parallel lines will never meet, and it will continue to expand indefinitely. These observations also support the theory of dark matter and dark energy, which dominate the universe but remain largely mysterious. Dark matter is believed to make up about 27% of the universe's total mass energy content, while dark energy, a force driving the accelerated expansion of the universe, accounts for roughly 68%. Understanding dark matter and dark energy is crucial to solving some of the most profound mysteries related to the Big Bang. Subscribe so you don't miss out on any of these videos. As the universe continued to expand and cool, gravity began to take hold, pulling together clouds of gas and dust to form stars and galaxies. The formation of the first stars, known as population 3 stars, is a critical milestone in cosmic history. These stars were made almost entirely of hydrogen and helium, the elements created during Big Bang nucleosynthesis. Heavier elements, such as carbon, oxygen, and iron, were forged later inside stars through nuclear fusion. When these stars died in supernova explosions, they seeded the universe with the elements needed to form planets, and, eventually, life. The large-scale structure of the universe, including galaxies, clusters of galaxies, and the vast cosmic web of dark matter, all originated from tiny fluctuations in the density of matter in the early universe. These fluctuations were amplified by gravity over billions of years, leading to the formation of the cosmic structures we observe today. The discovery of these large-scale structures is a triumph of the Big Bang model, but many questions remain about how galaxies formed and evolved. One of the great mysteries tied to the Big Bang is the concept of cosmic inflation and its implications for the multiverse hypothesis. If inflation occurred, it could have happened in different regions of space at different rates, creating bubble universes within a larger multiverse. Each bubble could have different physical laws, constants, and conditions, making our universe just one of many. While this idea is speculative, it opens up fascinating possibilities for understanding the nature of reality beyond our observable universe. Some versions of string theory also suggest the existence of a multiverse, with each universe having different dimensions and fundamental particles. The Big Bang theory has revolutionized our understanding of the universe, but it also raises profound philosophical and scientific questions. For example, what triggered the Big Bang? Some theories suggest a cyclical model in which the universe goes through repeated cycles of expansion and contraction, with each Big Bang followed by a Big Crunch. Others propose that the Big Bang was the result of a quantum fluctuation in a vacuum, with the universe spontaneously emerging from nothing. Yet, defining what nothing means in this context is itself a complex question, as quantum physics suggests that even in a vacuum, virtual particles can pop in and out of existence. Another area of active research is the nature of time itself. The Big Bang marks the beginning of time as we know it, but what does that mean? In general relativity, time is linked to the geometry of space, so if space began with the Big Bang, so did time. However, this creates paradoxes, such as what caused the Big Bang if there was no time before it. Some physicists suggest that time could be an emergent property, not a fundamental one, meaning that time itself may have arisen from the Big Bang just as space did. Understanding the nature of time is one of the most profound questions facing modern physics and philosophy. In recent years, advances in technology have allowed us to probe the universe further than ever before. Observatories such as the James Webb Space Telescope, JWST, aim to look back in time to the first galaxies and stars, offering a clearer picture of how the universe evolved after the Big Bang. Gravitational wave observatories like LIGO and Virgo have also opened a new window into the universe by detecting ripples in space-time caused by massive objects like black holes and neutron stars. These discoveries may provide crucial insights into the conditions of the early universe and how the Big Bang gave rise to the cosmos we see today. Another key aspect of the Big Bang theory involves understanding the role of dark matter and dark energy in shaping the universe's evolution. Dark matter, which makes up about 27% of the universe's total energy density, is invisible to our telescopes but exerts gravitational forces on galaxies and clusters of galaxies. This mysterious substance was essential in the formation of galaxies, providing the additional gravitational pull needed to bring gas and dust together in the early universe. However, dark matter doesn't interact with light, which means we cannot detect it directly. We infer its existence from the gravitational effects it has on visible matter, such as stars and galaxies. One of the great challenges of modern astrophysics is identifying what dark matter is composed of, with candidates ranging from weakly interacting massive particles, WIMPs, to more exotic particles like axions. While dark matter holds galaxies together, dark energy, which accounts for about 68% of the universe's energy content, is responsible for driving the universe's accelerated expansion. Discovered in the late 1990s through observations of distant supernovae, dark energy is one of the most profound mysteries in cosmology. It acts as a kind of repulsive force, counteracting gravity on cosmic scales and causing the universe to expand faster and faster. This accelerated expansion has led scientists to rethink the ultimate fate of the universe. If dark energy continues to dominate, the universe could experience a big freeze, where galaxies drift farther apart, stars burn out, and space becomes cold and dark. Another possibility is a big rip, in which dark energy becomes so strong that it tears galaxies, stars, and even atoms apart. These ideas about dark matter and dark energy are deeply connected to the Big Bang because they influence how the universe has evolved since its earliest moments. In the first few seconds after the Big Bang, the universe was dominated by radiation, particles of light that carried energy. As the universe expanded and cooled, matter began to dominate over radiation. Eventually, dark energy took over, leading to the current era of accelerated expansion. This transition from radiation to matter to dark energy domination is a key part of the Big Bang model and helps explain the universe's current structure. The Big Bang theory also explains the abundance of light elements in the universe. During the first few minutes after the Big Bang, temperatures were so high that nuclear fusion occurred, creating the lightest elements: hydrogen, helium, and small amounts of lithium. This process, known as Big Bang nucleosynthesis, produced about 75% hydrogen and 25% helium by mass, with trace amounts of other light elements. These predictions match the observed abundances of these elements in the universe today, providing strong evidence in favor of the Big Bang. Heavier elements, like carbon, oxygen, and iron, were created later inside stars through the process of stellar nucleosynthesis. One of the enduring mysteries of the Big Bang is the horizon problem, which asks why different regions of the universe, which are too far apart to have ever been in causal contact, have the same temperature and other properties. This problem arises because, in the standard Big Bang model, light and other signals could not have traveled between these regions in the time since the universe began, yet the cosmic microwave background shows that the universe is nearly uniform in all directions. Inflation theory solves this problem by proposing that the universe underwent a period of rapid expansion that stretched these regions out from a much smaller, causally connected area, leading to the uniformity we observe today. Another puzzle related to the Big Bang is the flatness problem. Observations show that the universe is nearly geometrically flat, meaning it is not curved like a sphere, closed, or like a saddle, open. However, for the universe to be flat today, it must have been extremely close to flat in its early moments. Even tiny deviations from flatness would have grown exponentially over time, leading to a universe that is either closed or open. Inflation theory again provides a solution by stretching any initial curvature of the universe to near flatness, much like how the surface of a balloon becomes flatter as it is inflated. Despite the successes of the Big Bang theory, there are still many open questions about the nature of the universe's earliest moments. One such question involves the singularity itself, the point of infinite density where the Big Bang began. According to general relativity, the equations governing spacetime break down at the singularity, meaning we cannot describe what happened at the exact moment of the Big Bang. To understand the singularity, we need a theory of quantum gravity, which would unite general relativity with quantum mechanics. Several candidates for such a theory exist, including string theory and loop quantum gravity, but none has yet been fully developed or experimentally verified. Another fascinating area of research is the possibility that the Big Bang was not a unique event. Some theories suggest that our universe could be part of a larger multiverse, with each universe undergoing its own Big Bang. In this view, the Big Bang may not represent the absolute beginning of everything but rather the beginning of our particular universe within a larger multiverse. These ideas are still speculative but have gained traction in theoretical physics as scientists explore the implications of cosmic inflation and string theory. One of the most intriguing ideas about the Big Bang is the possibility of a cyclical universe, where the universe goes through repeated cycles of expansion and contraction. In this model, the current expansion phase would eventually slow down and reverse, leading to a big crunch, where the universe collapses back into a hot, dense state. This could trigger another Big Bang, beginning a new cycle of cosmic evolution. While the idea of a cyclical universe is appealing, especially because it avoids the need for a singular beginning, current observations of dark energy and the universe's accelerated expansion suggest that a big crunch is unlikely, at least in the near future. The nature of time itself is another deep mystery tied to the Big Bang. According to our current understanding, time began with the Big Bang, meaning there was no before the Big Bang in the conventional sense. This idea challenges our everyday understanding of time as a linear sequence of events. Some physicists have proposed that time could be an emergent property, meaning that it arises from more fundamental processes in the same way that temperature emerges from the motion of particles in a gas. If time is emergent, then the Big Bang may not represent the absolute beginning of time, but rather a transition between different phases of the universe. Recent developments in quantum cosmology have also raised the possibility that the universe could have originated from a quantum fluctuation. In this view, the universe could have spontaneously appeared from a quantum vacuum, where virtual particles constantly pop in and out of existence. This idea challenges the notion that something cannot come from nothing, but in quantum mechanics, nothing is a much more complex concept than in classical physics. The quantum vacuum is not truly empty but filled with fluctuating energy, which could have given rise to the Big Bang. However, this idea is still speculative and remains an active area of research. Gravitational waves, ripples in space-time caused by massive objects like merging black holes, offer another avenue for exploring the Big Bang. The detection of these waves by the LIGO and Virgo observatories has opened a new way of studying the universe, including the possibility of detecting primordial gravitational waves. These waves would have been generated in the first moments of the Big Bang, and could provide direct evidence of inflation and other processes that occurred in the early universe. Detecting these primordial gravitational waves would be a groundbreaking discovery, offering a new window into the universe's birth. In recent years, experiments like the BICEP-2 project have sought to detect the imprint of primordial gravitational waves in the polarization of the cosmic microwave background. Although initial claims of detection were later attributed to dust in the Milky Way, the search for these waves continues, and future experiments could provide crucial evidence for inflation and other aspects of the Big Bang model. The discovery of primordial gravitational waves would not only confirm inflation but also help us understand the fundamental forces that govern the early universe. In the context of the Big Bang, gravitational waves represent more than just a fascinating side effect of cosmic collisions. They are a possible direct imprint of the universe's earliest moments. If these primordial gravitational waves are ever detected, they could offer insight into how energy transitioned into matter, how space-time itself behaved in the earliest instances after the universe's birth, and perhaps even reveal deeper truths about the forces that shaped cosmic evolution. One theory that arises in this context is the concept of quantum gravity. The nature of the Big Bang singularity, the infinitely dense point from which the universe supposedly emerged, cannot be fully explained by the equations of general relativity alone. At the extremely small scales near the moment of the Big Bang, quantum effects would have dominated, and we need a theory that unifies quantum mechanics with gravity to fully understand what occurred. Quantum gravity aims to bridge this gap, and one of the leading contenders is string theory, which posits that the fundamental building blocks of reality are not particles but rather tiny, vibrating strings of energy. In this view, the Big Bang may not have been a singular explosion from a point but rather a phase transition in a much larger, multidimensional space. This brings us to the idea of higher dimensions, and how they might play a role in the Big Bang. According to string theory, our universe may exist in a brane, a three-dimensional surface floating in a higher dimensional space. In this scenario, the Big Bang could have been caused by the collision of two branes, creating a burst of energy that ignited the creation of our universe. While this theory remains highly speculative, it offers a fascinating alternative to the traditional Big Bang model, suggesting that the birth of our universe may have been triggered by interactions in dimensions beyond our perception. The existence of higher dimensions also ties into the concept of the multiverse, a collection of many universes, each with its own set of physical laws. If our universe is just one of many, then the Big Bang might not represent the beginning of everything but rather the beginning of our particular bubble within the multiverse. In this view, other universes could have undergone their own Big Bangs, with different conditions leading to a wide variety of physical realities. Some universes might have different values for fundamental constants, making them uninhabitable or radically different from our own. While the multiverse hypothesis is still highly theoretical and lacks direct evidence, it has gained popularity in recent years as scientists attempt to explain some of the more puzzling features of our universe, such as the fine-tuning of physical constants that allow life to exist. One of the most intriguing implications of the multiverse theory is that it might offer a solution to the anthropic principle, which asks why the conditions of our universe are so finely tuned for life. In a multiverse, this fine-tuning might be a result of the fact that we happen to live in a universe where conditions allow life to arise. In other universes with different physical constants, life might be impossible, and there would be no observers to ask why those universes are the way they are. While this explanation is speculative, it provides a potential answer to one of the biggest philosophical questions raised by the Big Bang. Returning to the more observational aspects of the Big Bang, another major breakthrough in recent years has been the study of the cosmic microwave background, CMB, in greater detail. The CMB, which is often described as the afterglow of the Big Bang, provides a snapshot of the universe when it was just 380,000 years old, before stars, galaxies, or any other large structures had formed. By studying the tiny fluctuations in the temperature and polarization of the CMB, scientists can learn about the conditions in the early universe and test predictions made by the Big Bang model and inflationary theory. For example, the Planck satellite, launched in 2009, provided the most detailed map of the CMB to date, confirming many aspects of the standard cosmological model, while also raising new questions about the universe's composition and geometry. One of the challenges of studying the Big Bang is the fact that we can only observe the aftermath of the event, not the event itself. While the CMB offers a glimpse of the universe when it was still very young, it doesn't take us all the way back to the singularity. To probe earlier times, scientists rely on a combination of theoretical models and indirect observations, such as the distribution of galaxies and the large-scale structure of the universe. These observations provide clues about the initial conditions of the universe and the processes that shaped its evolution, but they also leave many unanswered questions. For example, why did the universe transition from a hot, dense state to a more structured, complex state? What caused the initial fluctuations in density that eventually led to the formation of galaxies and galaxy clusters? In addition to these observational challenges, the Big Bang theory faces conceptual challenges as well. One of the most significant is the nature of the singularity itself. In classical physics, a singularity is a point where physical quantities become infinite, such as density, temperature, and pressure. However, infinities are typically a sign that a theory has broken down, indicating that we need a new framework to describe what happens in such extreme conditions. This is where the need for a theory of quantum gravity becomes crucial, as it would allow us to understand the behavior of spacetime and matter in the vicinity of the singularity. Some theories, such as loop quantum gravity, suggest that the Big Bang may not have been a singularity at all but rather a bounce from a previous contracting phase of the universe. In this view, the universe undergoes cycles of expansion and contraction, with the Big Bang marking the transition from one phase to the next. Another theoretical challenge is understanding how the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, unified in the earliest moments of the Big Bang. According to current models, the universe began in a state of extremely high energy, where all the forces were unified into a single, overarching force. As the universe expanded and cooled, these forces broke apart, into the distinct forces we observe today. This process, known as symmetry breaking, is a key aspect of the Big Bang model, but it remains poorly understood. In particular, scientists are still searching for a unified theory that can describe how these forces behave at the highest energies. Such a theory, often referred to as a theory of everything, would not only explain the behavior of the universe in its earliest moments, but also offer deeper insights into the nature of reality itself. One of the most profound implications of the Big Bang theory is the idea that the universe had a beginning, a point in time when space and time themselves came into existence. This notion challenges our everyday understanding of causality, where every event has a cause. If the universe had a beginning, what caused the Big Bang? Some theories suggest that the universe could have arisen spontaneously from a quantum fluctuation in a pre-existing state, while others propose that the Big Bang was the result of a collision between higher-dimensional branes or a phase transition in a larger multiverse. These ideas, while speculative, raise fundamental questions about the nature of time, causality, and the origins of the universe. In addressing the idea of the Big Bang as the beginning of time, one of the most perplexing questions arises: what existed before the Big Bang? The very concept of before becomes problematic because time, as we understand it, was born with the Big Bang. This challenges our intuitive notions of cause and effect, where every event must have a preceding cause. In the realm of cosmology, the question of what came before the Big Bang is fundamentally linked to the nature of time itself. If time did not exist before the Big Bang, then asking what came before it might not even be a meaningful question within our current understanding of physics. However, some theories do attempt to address the notion of a pre-Big Bang state. One such idea is that the Big Bang was not the absolute beginning but rather a transition from a previous state of the universe. For example, in the cyclic model of the universe, the Big Bang could have been the result of the collapse of a previous universe. In this model, the universe undergoes infinite cycles of expansion and contraction, with each Big Bang marking the end of one cycle and the beginning of the next. This model provides an elegant way to avoid the singularity problem and offers a potential explanation for why the universe appears to be expanding today. However, it also raises new questions, such as what causes the transition between contraction and expansion, and whether there is any empirical evidence for such cycles. Another proposal is the idea of the multiverse, where our universe is just one of many that exist in a larger cosmic landscape. In this view, the Big Bang may have been the creation of our specific universe, but other universes could have been created through their own Big Bangs in other regions of the multiverse. Some versions of this theory suggest that different universes might have different physical constants and laws of physics, leading to a wide variety of possible outcomes. Our universe, with its particular set of physical laws, may be just one of many possible configurations in the multiverse. This idea, while still speculative, has gained traction in recent years as scientists attempt to explain certain puzzling aspects of our universe, such as the fine-tuning of physical constants that allow life to exist. The idea of a multiverse also raises philosophical questions about the nature of reality. If our universe is just one of many, what does that say about the significance of our own existence? Are we just one tiny part of a much larger, infinitely diverse collection of realities? And if so, how does that affect our understanding of concepts like space, time, and causality? These questions, while speculative, push the boundaries of our understanding of the universe and highlight the profound mysteries that still surround the Big Bang. One of the key challenges in studying the Big Bang is the fact that we are limited in what we can observe. As mentioned earlier, the cosmic microwave background (CMB) provides a snapshot of the universe when it was just 380,000 years old, but it doesn't take us all the way back to the singularity. In fact, the earliest moments of the universe are hidden from us, as the universe was opaque to radiation before the formation of the CMB. This means that direct observations of the first few moments after the Big Bang are currently impossible, and scientists must rely on indirect evidence and theoretical models to infer what happened. One of the key pieces of indirect evidence for the Big Bang comes from the large-scale structure of the universe. By studying the distribution of galaxies and galaxy clusters, scientists can infer the initial conditions of the universe and how it evolved over time. For example, the fact that galaxies are distributed in a cosmic web of filaments and voids suggests that the universe began with small fluctuations in density, which later grew into the large structures we see today. These fluctuations are thought to have been caused by quantum fluctuations in the early universe, which were stretched to macroscopic scales by the process of cosmic inflation. By studying the distribution of galaxies and the cosmic web, scientists can test predictions made by the Big Bang model and gain insights into the universe's early history. Another important piece of evidence comes from the abundance of light elements in the universe, such as hydrogen, helium, and lithium. According to the Big Bang nucleosynthesis theory, these elements were formed in the first few minutes after the Big Bang, when the universe was hot and dense enough for nuclear reactions to occur. The relative abundances of these elements provide a powerful test of the Big Bang model, as they depend on the conditions that existed in the early universe. Observations of the abundance of light elements in the universe are in excellent agreement with the predictions of the Big Bang model, providing strong evidence that the universe did indeed begin in a hot, dense state. While the Big Bang model has been remarkably successful in explaining many aspects of the universe, it is not without its challenges. One of the biggest challenges is the nature of dark matter and dark energy, which together make up about 95% of the total mass energy content of the universe. Dark matter is thought to be a form of matter that does not interact with light, making it invisible to telescopes. However, its presence can be inferred from its gravitational effects on galaxies and galaxy clusters. Dark energy, on the other hand, is a mysterious force that is causing the expansion of the universe to accelerate. While the Big Bang model can account for the overall structure of the universe, it does not currently explain the nature of dark matter and dark energy, which remain two of the biggest unsolved mysteries in cosmology. The discovery of dark energy in the late 1990s was one of the most surprising findings in modern cosmology. Prior to this discovery, scientists had expected that the expansion of the universe would slow down over time, due to the gravitational pull of matter. However, observations of distant supernovae revealed that the universe's expansion is actually speeding up, leading to the conclusion that a mysterious form of energy, dark energy, must be driving this acceleration. The nature of dark energy remains unknown, but one possibility is that it is related to the energy of empty space, also known as the cosmological constant. This idea was first proposed by Albert Einstein as a modification to his equations of general relativity, but he later abandoned it, calling it his biggest blunder. However, the discovery of dark energy has led to a resurgence of interest in the cosmological constant as a possible explanation for the universe's accelerating expansion. Another possibility is that dark energy is related to a new, unknown field, similar to the field responsible for cosmic inflation. This field could have a dynamic nature, changing over time and affecting the expansion rate of the universe in different ways. Some theories even suggest that dark energy could be a sign that our understanding of gravity is incomplete, and that new physics is needed to explain the behavior of the universe on large scales. The mystery of dark energy is compounded by the fact that it appears to be uniformly distributed throughout the universe, exerting its influence in every corner of space. Unlike ordinary matter, which clumps together to form galaxies, stars, and planets, dark energy seems to be a constant background force that pervades the cosmos. This uniformity leads to a profound question: why does dark energy exist at all, and why is it so perfectly balanced? The amount of dark energy in the universe is incredibly small compared to the energy densities we are familiar with on Earth, but its cumulative effect over vast cosmic distances leads to the accelerated expansion of the universe. This precise balance has led some scientists to wonder whether there is some deeper, underlying principle that governs the existence of dark energy, or whether its value is simply a coincidence in our universe's history. The concept of the fine-tuning of the universe also extends to the Big Bang itself. The initial conditions of the universe appear to be extraordinarily precise, leading some to speculate whether the universe was designed to support life. For example, if the density of matter and energy in the early universe had been only slightly different, the universe might have collapsed in on itself in a big crunch, or expanded too quickly for galaxies and stars to form. Similarly, the strength of the fundamental forces of nature, gravity, electromagnetism, the strong and weak nuclear forces, must fall within very narrow ranges for the universe to be capable of supporting life. This apparent fine-tuning has led to the idea of the anthropic principle, which suggests that the universe appears fine-tuned for life simply because we exist to observe it. In other words, if the universe were not capable of supporting life, we wouldn't be here to notice. The anthropic principle, while philosophically interesting, doesn't provide a physical explanation for why the universe is fine-tuned. This has led some scientists to propose that the fine-tuning of the universe could be explained by the multiverse. In a multiverse scenario, there could be many different universes, each with its own set of physical constants. Most of these universes might be barren and lifeless, but we happen to live in one that is capable of supporting life because it has the right combination of constants. This idea provides a potential solution to the fine-tuning problem, but it also raises new questions. If there are multiple universes, how can we detect them? And if we can't, is the multiverse a scientifically valid concept, or is it merely a philosophical speculation? These questions about dark energy, fine-tuning, and the multiverse highlight the fact that the Big Bang Theory, while incredibly successful, is not the final word on the origin and nature of the universe. Instead, it represents our best current understanding, based on the evidence available to us. But as new observations are made and new theories are developed, our understanding of the Big Bang and the cosmos as a whole will continue to evolve. One area of ongoing research is the study of the early universe, particularly the first few moments after the Big Bang. While the cosmic microwave background gives us a snapshot of the universe at 380,000 years old, scientists are working to probe even earlier epochs, when the universe was just a fraction of a second old. This period, known as the Planck epoch, is thought to be governed by quantum gravity, where the effects of both general relativity and quantum mechanics become important. However, we currently lack a complete theory of quantum gravity, making it difficult to fully understand the physics of the Planck epoch. One candidate theory for quantum gravity is string theory, which posits that the fundamental building blocks of the universe are not point-like particles but tiny, vibrating strings. String theory has the potential to unify all the forces of nature, including gravity, under a single theoretical framework. In the context of the Big Bang, string theory could provide insights into the nature of the singularity, and what, if anything, existed before it. Some versions of string theory also predict the existence of extra dimensions of space, beyond the three spatial dimensions we experience. These extra dimensions could have played a role in the early universe and might offer new ways to understand the Big Bang. In addition to string theory, another approach to understanding the early universe is through the study of quantum cosmology. This field attempts to apply the principles of quantum mechanics to the entire universe, rather than just individual particles. In this framework, the Big Bang could be understood as a quantum event, where the universe emerged from a quantum state of nothingness. One model of quantum cosmology is the no-boundary proposal, developed by physicists Stephen Hawking and James Hartle. In this model, the universe has no initial boundary or edge in time. Instead, time itself becomes rounded off, in the early universe, like the surface of a sphere. In this view, the universe has no beginning in the traditional sense, as time becomes indistinguishable from space at very early times. While these ideas are speculative, they represent promising avenues for future research and could potentially lead to a deeper understanding of the Big Bang. However, testing these theories is extremely challenging, as the conditions of the early universe are difficult to recreate or observe. One possibility is that experiments with high-energy particle accelerators, such as the Large Hadron Collider, LHC, could provide clues about the fundamental nature of the universe and the forces that governed its early evolution. By smashing particles together at extremely high energies, scientists can recreate conditions similar to those that existed just moments after the Big Bang, allowing them to probe the fundamental building blocks of matter and energy. Another promising avenue of research is the study of gravitational waves, ripples in the fabric of space-time caused by violent cosmic events. The detection of gravitational waves by the LIGO and Virgo observatories has opened up a new way of studying the universe, providing insights into phenomena such as black hole mergers and neutron-star collisions. Some theories suggest that gravitational waves could also carry information about the early universe, including the period of cosmic inflation. If we can detect gravitational waves from the Big Bang itself, it could provide direct evidence of the universe's rapid expansion in its earliest moments, and help us better understand the physics of inflation. The study of gravitational waves and high-energy particle physics also intersects with another major mystery of the Big Bang: the nature of the singularity itself. As mentioned earlier, the singularity represents a point of infinite density and temperature, where the laws of physics as we know them break down. This presents a profound challenge for physicists, as it suggests that our current understanding of the universe is incomplete. One possibility is that the singularity is not a true physical entity but rather a sign that we need a new framework for understanding the universe at extremely small scales. Some theories suggest that quantum effects could smear out the singularity, preventing it from reaching infinite density. Others propose that the singularity could be replaced by a quantum bounce, where the universe undergoes a contraction followed by a rebound into expansion. These ideas are still in the early stages of development, and much more work is needed to determine whether they can provide a complete explanation of the Big Bang. However, they highlight the fact that the study of the universe's origin is far from over. As we continue to push the boundaries of our understanding, we may one day uncover new insights into the deepest mysteries of the cosmos. The concept of the singularity and its resolution is at the frontier of modern physics. One of the key challenges in this area is developing a theory that can unify the physics of the very large, general relativity, with the physics of the very small, quantum mechanics. This is where quantum gravity theories come into play, as they aim to describe the behavior of gravity at quantum scales, particularly at the extremely high densities and temperatures that existed in the first moments of the Big Bang. Loop quantum gravity is another theory that attempts to resolve the singularity issue. Unlike string theory, which relies on tiny vibrating strings to explain fundamental particles, loop quantum gravity focuses on quantizing spacetime itself. In this framework, spacetime is not continuous but consists of discrete, tiny loops, or quanta, of spacetime, much like matter is made up of atoms. One of the predictions of loop quantum gravity is that, rather than the universe beginning with a singularity, the Big Bang might have been preceded by a big bounce. In this scenario, the universe could have existed in a previous state of contraction before reaching a minimum size and then bouncing outward in the expansion we now observe. This cyclic model eliminates the need for an initial singularity and offers an intriguing alternative to traditional Big Bang cosmology. The idea of a big bounce is not limited to loop quantum gravity. Some versions of string theory, particularly those that consider higher-dimensional, brane, worlds, also allow for a bouncing universe. In these models, our universe could be a three-dimensional, brane, floating in a higher-dimensional space. Collisions between branes in this higher-dimensional space could trigger repeated cycles of expansion and contraction, with each bang leading to the formation of a new universe. This concept, often referred to as brane cosmology, provides a framework for understanding the Big Bang not as a unique event but as part of a larger, ongoing cosmic cycle. These bouncing models address one of the long-standing questions in cosmology: what, if anything, existed before the Big Bang? In traditional Big Bang theory, the singularity represents the beginning of time, so it is impossible to talk about before in any meaningful sense. However, if the universe underwent a bounce, there would have been a previous phase of contraction, and possibly many such cycles before that. This leads to the possibility that the universe has no true beginning. It has been cycling through phases of expansion and contraction for an infinite amount of time. While this idea is compelling, it remains speculative, as we currently have no direct evidence for a pre-Big Bang phase or for any cyclic behavior in the universe's history. One challenge with cyclic models is explaining how the universe can expand and contract repeatedly without running into problems. In particular, the second law of thermodynamics, which states that the total entropy disorder of a closed system must always increase seems to imply that each successive cycle of the universe would become more disordered than the last. Eventually, the universe would reach a state of maximum entropy, or heat death, where no further cycles could occur. Some theories attempt to resolve this issue by proposing that each bounce resets the entropy of the universe, allowing for an infinite number of cycles. Others suggest that new physical processes could emerge during each contraction that would reverse the effects of entropy buildup. However, these ideas are still highly speculative and face significant theoretical challenges. Another major mystery related to the Big Bang is the question of why the universe is so homogeneous and isotropic, that is, why it looks roughly the same in all directions. This is known as the horizon problem. According to standard Big Bang theory, different regions of the universe should not have been in causal contact with each other early on, meaning there was no way for them to communicate and reach the same temperature and density. Yet when we look at the cosmic microwave background, we see that the universe is incredibly uniform on large scales, with only tiny fluctuations in temperature. This uniformity suggests that there must have been some process that allowed different regions of the universe to come into equilibrium with each other before the Big Bang. The most widely accepted solution to the horizon problem is the theory of cosmic inflation, which was first proposed by physicist Alan Guth in the early 1980s. Inflation posits that in the first fraction of a second after the Big Bang, the universe underwent a period of extremely rapid expansion, growing by a factor of at least 10 to the power of 26 in less than a trillionth of a second. This rapid expansion stretched out any initial irregularities in the universe, smoothing them over and creating the homogeneity we observe today. Inflation also provides an explanation for the origin of the tiny density fluctuations that later grew into galaxies and large-scale cosmic structures. These fluctuations are thought to arise from quantum fluctuations in the fabric of spacetime itself, which were magnified by inflation and frozen into the universe's structure as it expanded. While inflation is a powerful and widely accepted theory, it is not without its challenges. One issue is that the mechanism that drives inflation is still not fully understood. The theory requires the existence of a hypothetical field, known as the inflaton field, which would have provided the necessary energy to drive the universe's rapid expansion. However, the exact nature of this field and how it relates to the known forces of nature remains unclear. Some versions of inflation theory also predict that inflation could continue indefinitely in some regions of the universe, leading to the idea of eternal inflation. In this scenario, while inflation ended in our region of the universe, it continues in other regions, creating an ever-expanding multiverse. Each pocket of the multiverse could have different physical properties, leading to a diversity of possible universes with different laws of physics. The idea of eternal inflation ties into the broader concept of the multiverse, which has become an increasingly popular topic in both theoretical physics and popular science. The multiverse hypothesis suggests that our universe is just one of many, each with its own set of physical laws and constants. While the multiverse offers a potential explanation for why our universe appears fine-tuned for life, it also raises profound philosophical and scientific questions. If other universes exist, can we ever detect them? And if we cannot, does the multiverse hypothesis fall outside the realm of scientific inquiry? The multiverse is not the only alternative to the traditional Big Bang model. Some physicists have explored other possibilities, such as the idea that the universe could have originated from a quantum fluctuation in a vacuum. In this view, the universe could have emerged spontaneously from a state of nothingness, driven by the principles of quantum mechanics. This idea, often referred to as quantum creation, suggests that the universe does not require a cause in the traditional sense. Instead, it could have arisen naturally from the probabilistic nature of quantum events. While this concept is difficult to test experimentally, it provides a way to think about the origin of the universe without invoking a singularity or a pre-existing cause. As we continue to explore these mysteries, it is clear that the Big Bang is just the beginning of the story. The origin of the universe, the nature of dark energy and dark matter, the possibility of a multiverse, and the resolution of the singularity all represent deep, unanswered questions that challenge our understanding of the cosmos. Each of these mysteries pushes the boundaries of human knowledge, inviting us to look deeper into the fabric of reality and question our assumptions about space, time, and existence itself. The Big Bang Theory also raises profound questions about the nature of time itself. In our everyday experience, time seems to flow continuously from the past to the future, governed by the arrow of time and the progression of events. However, the Big Bang brings this understanding into question. At the singularity, where all the known laws of physics break down, time as we know it ceases to exist in a meaningful way. If the Big Bang represents the origin of the universe, it also marks the origin of time itself, since there was no before, in the conventional sense. This idea is difficult to comprehend because it challenges our intuitive sense of cause and effect. Einstein's theory of general relativity, which describes how gravity shapes the structure of space and time, fundamentally altered our understanding of time. According to relativity, time is not a separate, independent entity but is intertwined with space to form a four-dimensional fabric known as spacetime. The presence of mass and energy warps spacetime, creating the effect we perceive as gravity. At the Big Bang, the density of the universe was so extreme that spacetime itself was curved to an infinite degree. In this scenario, time and space are no longer distinct entities but become merged in ways that defy our everyday understanding. One of the great unsolved problems in modern physics is how to reconcile the nature of time as described by general relativity with the probabilistic nature of time in quantum mechanics. In quantum mechanics, time is treated as an independent parameter that ticks forward uniformly, unaffected by the dynamics of space or matter. This treatment works well at the microscopic scale of particles, but it is at odds with the relativistic description of time, where the passage of time can vary depending on the gravitational field and the observer's relative motion. The search for a theory that unifies general relativity with quantum mechanics, a theory of quantum gravity, is one of the most significant challenges facing theoretical physicists today. Such a theory would not only help us understand the Big Bang more fully but might also provide insights into the true nature of time and the universe itself. There are various approaches being explored in the quest for quantum gravity, including string theory and loop quantum gravity, as previously mentioned. Both of these theories attempt to address the singularity at the heart of the Big Bang by introducing new concepts of space and time at the quantum scale. In string theory, for example, time and space emerge from the vibrations of fundamental strings, with different vibrational patterns corresponding to different particles and forces. In loop quantum gravity, space and time are quantized, meaning that they are made up of tiny, discrete units, much like matter is made up of atoms. If time is quantized, then the flow of time might not be smooth and continuous as we experience it, but rather it could jump between different states, much like a clock ticking. Another approach to understanding the nature of time in the context of the Big Bang is the study of thermodynamics and entropy. The second law of thermodynamics, which states that the total entropy of a closed system must always increase over time, gives rise to the arrow of time, the idea that time flows in one direction, from past to future. At the Big Bang, the universe began in an extremely low entropy state, with matter and energy distributed very uniformly. As the universe has expanded, entropy has increased, leading to the formation of stars, galaxies, and complex structures. This increasing entropy is what drives the forward progression of time. However, some physicists have speculated that if the universe undergoes a future phase of contraction, as in cyclic models or the Big Bounce, time might reverse its direction, and entropy might decrease. While this idea remains speculative, it highlights the deep connection between thermodynamics and our understanding of time. One of the most perplexing questions related to the Big Bang is why the universe began in such a low entropy state in the first place. This question is known as the past hypothesis, and is central to our understanding of the arrow of time. If the universe had started in a higher entropy state, then time might not have had a clear direction, and the evolution of the universe would have been very different. Some physicists believe that the low entropy beginning of the universe could be a clue to a deeper underlying principle, perhaps related to the initial conditions of the universe, or the nature of spacetime itself. Others suggest that the low-entropy state could be the result of quantum processes during the early moments of the Big Bang, where quantum fluctuations determined the initial configuration of matter and energy. In addition to these questions about time and entropy, the Big Bang theory also raises important questions about the geometry and fate of the universe. Cosmologists have long debated the ultimate fate of the universe, whether it will continue expanding forever, eventually slow down and collapse in a big crunch, or reach a state of equilibrium in which expansion halts. The geometry of the universe plays a key role in determining its fate. According to general relativity, the geometry of spacetime can be described as flat, open, or closed, depending on the total amount of mass and energy in the universe. In a flat universe, which appears to be the case based on current observations, the expansion will continue indefinitely, but at an ever-slowing rate. In an open universe, the expansion will accelerate, and the universe will eventually become cold and dark as galaxies recede beyond the observable horizon. This scenario is sometimes referred to as the Big Freeze, or heat death, where the universe reaches a state of maximum entropy, and all thermodynamic processes come to an end. In a closed universe, the expansion would eventually stop, and the universe would begin to contract, potentially leading to a future big crunch, where all matter and energy are compressed back into a singularity. However, the discovery of dark energy in the late 20th century has complicated this picture. Dark energy is a mysterious form of energy that appears to be driving the accelerated expansion of the universe. It makes up about 70% of the total energy content of the universe, with dark matter accounting for about 25%, and ordinary matter, the stuff we see in stars, planets, and galaxies, making up only about 5%. The nature of dark energy remains one of the biggest mysteries in cosmology. If dark energy continues to dominate, the universe could enter a phase of eternal inflation, where the accelerated expansion never stops, and the universe becomes increasingly empty and isolated. One of the strangest possibilities related to dark energy is the idea of the Big Rip. In this scenario, the repulsive force of dark energy could become so strong that it overcomes all other forces in the universe, tearing apart galaxies, stars, planets, and even atoms. The Big Rip would represent the ultimate end of the universe, where the very fabric of spacetime itself is torn apart. While this scenario is speculative, it highlights the profound influence that dark energy has on our understanding of the universe's fate. The Big Bang theory also forces us to confront the limits of our knowledge. While the theory provides a powerful framework for understanding the evolution of the universe from its earliest moments to the present day, it leaves many fundamental questions unanswered. What caused the Big Bang? Why did the universe begin in such a low entropy state? What is the nature of dark matter and dark energy? Is the universe part of a larger multiverse? These questions push the boundaries of human knowledge and challenge our ability to probe the deepest mysteries of existence. In recent years, advances in observational technology have provided new ways to test and refine our understanding of the Big Bang and the early universe. The discovery of gravitational waves, ripples in spacetime caused by violent cosmic events like the collision of black holes, has opened a new window into the universe's history. Future gravitational wave detectors may be able to detect signals from the very early universe, potentially shedding light on the physics of the Big Bang itself. Likewise, new observations of the cosmic microwave background, the faint afterglow of the Big Bang, continue to provide insights into the universe's initial conditions and the process of inflation. Despite these advances, many aspects of the Big Bang theory remain beyond the reach of current experiments. The extremely high energies and densities that characterize the universe in its first moments are far beyond anything we can recreate in particle accelerators. However, ongoing research in fields like particle physics, quantum mechanics, and cosmology holds the promise of new breakthroughs that could revolutionize our understanding of the universe's origins. The future of our understanding of the Big Bang is closely tied to developments in particle physics, particularly in the study of high-energy particles and their interactions. One of the key goals of modern physics is to probe conditions that resemble the earliest moments of the universe, when the fundamental forces of nature were unified. The Large Hadron Collider, LHC, the world's largest and most powerful particle accelerator, has provided crucial insights into the nature of matter and energy by smashing protons together at incredibly high speeds, creating conditions similar to those just after the Big Bang. One of the most significant discoveries from the LHC was the detection of the Higgs boson in 2012, a particle that gives other particles mass. The Higgs field, associated with the Higgs boson, is thought to have played a vital role in the early universe, particularly in the phase known as electroweak symmetry breaking. Before this phase transition, the electromagnetic force and the weak nuclear force were indistinguishable from one another. As the universe cooled, the Higgs field switched on, giving mass to elementary particles and allowing the forces to differentiate. This discovery confirmed a key part of the standard model of particle physics, but it also raised new questions about the role of the Higgs field in the Big Bang and the nature of the vacuum in which the universe exists. The study of particle physics also touches on one of the most profound and enigmatic questions in cosmology: the matter-antimatter asymmetry. According to the Big Bang theory, matter and antimatter should have been created in equal amounts in the early universe. Yet we observe a universe dominated by matter, with very little antimatter present. This imbalance is known as baryon asymmetry, and it remains a major puzzle in physics. If matter and antimatter had annihilated each other in equal amounts, the universe would be filled with nothing but energy, leaving no matter to form stars, planets, or life. So why does matter exist at all? Various theories have been proposed to explain the matter-antimatter asymmetry. One possibility involves a phenomenon known as CP violation, which refers to small differences in the behavior of particles and antiparticles that could lead to an excess of matter over time. Experimental evidence for CP violation has been found in certain particle interactions, but it is not yet clear if this effect is strong enough to explain the observed asymmetry. Other theories suggest that unknown processes during the early universe, such as interactions between dark matter and ordinary matter, could have contributed to the imbalance. Understanding the origins of this asymmetry could provide critical insights into the conditions that prevailed during the Big Bang and the laws of physics that govern our universe. Another frontier in the study of the Big Bang is the investigation of cosmic inflation, the rapid expansion of space that occurred in the first fraction of a second after the universe began. While inflation theory has successfully explained many features of the universe, such as its large-scale uniformity and the distribution of galaxies, the precise mechanism that drove inflation remains unknown. One of the key goals of cosmologists is to find direct evidence of inflation, which could take the form of primordial gravitational waves, ripples in space-time generated by the intense expansion. These gravitational waves would leave a faint imprint on the cosmic microwave background, the oldest light in the universe, in the form of tiny fluctuations in polarization. Several experiments are currently searching for this signature, including the BICEP and Planck satellite missions. While no definitive detection has been made yet, the discovery of primordial gravitational waves would be a major breakthrough, providing direct evidence of the inflationary period and offering clues about the physics that govern the universe at its birth. Such a discovery would also have profound implications for our understanding of the quantum nature of spacetime, as it would provide insights into how quantum fluctuations during inflation seeded the structures we see in the universe today. The nature of dark matter, which makes up about 25% of the universe's total mass energy content, is another key area of investigation linked to the Big Bang. Dark matter is invisible and does not interact with light, making it difficult to detect directly, but its gravitational influence is observable in the motions of galaxies and the large-scale structure of the universe. The leading candidates for dark matter are particles that were created in the hot, dense conditions of the early universe. These particles, known as WIMPs, weakly interacting massive particles, would have been produced in large quantities during the Big Bang and remain present in the universe today, forming a kind of cosmic scaffolding that shapes the formation of galaxies and clusters. Several experiments, including direct detection experiments like LUX Zeppelin and indirect searches using gamma-ray telescopes, are actively searching for evidence of dark matter particles. While no definitive detection has been made, the study of dark matter continues to be a major focus in both particle physics and cosmology. Understanding the nature of dark matter could provide crucial insights into the physics of the early universe and the processes that shaped its evolution. In addition to dark matter, the discovery of dark energy in the 1990s has further complicated our understanding of the universe's fate. Dark energy, which makes up roughly 70% of the universe's total energy content, appears to be driving the accelerated expansion of the universe. While dark energy is often modeled as a form of vacuum energy associated with empty space, its true nature remains a profound mystery. Some theories suggest that dark energy could be related to the cosmological constant, a term introduced by Einstein in his equations of general relativity, while others propose more exotic explanations, such as dynamic fields that evolve over time. The existence of dark energy has profound implications for the future of the universe, as it suggests that the expansion will continue to accelerate, eventually leading to a cold, empty universe in which galaxies drift apart and stars burn out. This scenario, known as the Big Freeze, represents one possible end to the universe. However, if dark energy is not constant but changes over time, it could lead to different outcomes, such as a future phase of contraction or even a catastrophic event like the Big Rip, where space itself is torn apart. The study of the universe's expansion is also closely linked to the concept of the Hubble constant, which describes the rate at which galaxies are receding from each other due to the expansion of space. Recent measurements of the Hubble constant have revealed a puzzling discrepancy. Different methods of measuring the expansion rate give slightly different values. This Hubble tension suggests that there may be something missing from our understanding of cosmology, perhaps related to the nature of dark energy, dark matter, or the physics of the early universe. Resolving this tension is a major goal of modern cosmology, and could lead to new insights into the Big Bang and the evolution of the universe. As we continue to explore the mysteries of the Big Bang, one of the most intriguing possibilities is the idea that our universe is just one of many in a vast multiverse. In some versions of inflation theory, the rapid expansion of space during the early moments of the Big Bang could have created multiple bubble universes, each with its own distinct properties and physical laws. Our universe would be just one of these bubbles, and there could be countless others beyond our observable horizon. The multiverse hypothesis, while speculative, offers a potential explanation for the fine-tuning of physical constants in our universe. It suggests that different universes could have different values for fundamental parameters, such as the strength of gravity or the masses of particles, and that we happen to live in a universe where the conditions are right for life to exist. While the multiverse remains a controversial idea, it has gained traction in recent years as a possible solution to the deep puzzles of cosmology. If true, the multiverse would challenge our understanding of the Big Bang as a singular event, instead suggesting that our universe is just one of many in an ever-expanding cosmic landscape. However, testing the multiverse hypothesis is extremely difficult, as other universes would likely be beyond the reach of any observational tools we can develop. Nevertheless, the concept of the multiverse raises profound philosophical and scientific questions about the nature of reality and our place in the cosmos. The Big Bang Theory, with all its complexity and mystery, remains one of the most successful and compelling explanations for the origin of the universe. It has transformed our understanding of the cosmos, from the tiniest subatomic particles to the largest structures in the universe, and it continues to drive the frontiers of physics and astronomy. As we probe deeper into the mysteries of the Big Bang, we are likely to encounter new challenges and surprises that will reshape our understanding of the universe and its origins. As our understanding of the Big Bang Theory deepens, one of the most profound questions we face is the relationship between quantum mechanics and general relativity. These two fundamental pillars of physics describe different aspects of reality, with quantum mechanics governing the behavior of particles on the smallest scales, and general relativity explaining the dynamics of space-time and gravity on large scales. While both theories have been incredibly successful in their respective domains, they remain incompatible with each other. This incompatibility becomes particularly apparent when we try to describe the very early universe, where both quantum and gravitational effects were equally important. In this sense, the Big Bang represents a frontier where our current understanding of physics breaks down, pointing to the need for a deeper theory that can unify quantum mechanics and gravity. One promising candidate for such a theory is string theory, which posits that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings of energy. These strings can take on different vibrational modes, corresponding to different particles, and their interactions could, in theory, reconcile quantum mechanics and gravity. In string theory, gravity is described by the exchange of hypothetical particles called gravitons, which arise naturally from the vibrational patterns of strings. String theory also introduces extra dimensions beyond the familiar 3 dimensions of space and 1 of time, suggesting that the universe we experience is just a small part of a much larger, multidimensional reality. In the context of the Big Bang, string theory could offer explanations for some of the deepest mysteries of the early universe. For example, it provides a framework for understanding the extremely high-energy conditions that existed at the moment of the Big Bang, where the energies involved were far beyond anything we can currently produce in particle accelerators. String theory also suggests that the Big Bang might not have been a singularity at all, but rather the result of a collision between higher-dimensional branes, short for membranes, in a larger multidimensional space. This idea, known as the ekpyrotic universe model, offers an alternative to the traditional Big Bang scenario, in which the universe begins from a single point. Instead, the collision of branes could have triggered the expansion of the universe, with the energy from the collision giving rise to the matter and radiation we observe today. The ekpyrotic model is still speculative, but it highlights how string theory could offer new insights into the nature of the Big Bang and the origin of the universe. It also raises intriguing possibilities for what might have existed before the Big Bang. In traditional cosmology, the question of before the Big Bang is often considered meaningless, since time itself is thought to have begun at the moment of the Big Bang. However, in the ekpyrotic model and other theories inspired by string theory, the universe could have existed in some form before the Big Bang, perhaps as part of an eternal cycle of expansion and contraction. This idea, known as the cyclic universe, suggests that the Big Bang was not a unique event, but rather part of a repeating process in which the universe periodically collapses and re-expands. While the cyclic universe model is still highly speculative, it offers a possible solution to some of the puzzles of the Big Bang, such as the question of what caused the initial expansion. In the cyclic model, each cycle of collapse and re-expansion could be driven by the interplay of fundamental forces, such as gravity and dark energy, with the Big Bang representing the moment of transition between cycles. This idea also challenges the traditional view of the universe as having a definite beginning and end, suggesting instead that the universe could be eternal, with no ultimate starting point or final destination. Another approach to understanding the Big Bang involves the concept of quantum gravity, which seeks to describe gravity using the principles of quantum mechanics. One of the most well-known theories of quantum gravity is loop quantum gravity, which suggests that space-time itself is quantized, meaning that it is made up of discrete units, rather than being continuous. In this view, the fabric of space-time is composed of tiny loops, which form a kind of network that gives rise to the structure of the universe. Loop quantum gravity offers a possible explanation for what happened at the Big Bang, as it suggests that the singularity predicted by classical general relativity could be avoided. Instead, the universe could have undergone a bounce, in which it contracted to a very small, but finite size, before expanding again in the Big Bang. The idea of a cosmic bounce is appealing because it could resolve some of the paradoxes associated with the Big Bang, such as the infinite density and temperature predicted by classical theories. In loop quantum gravity, the quantization of spacetime prevents these infinities from occurring, suggesting that the universe could have passed through a previous phase of contraction before entering the current phase of expansion. This concept of a bouncing universe is still under active investigation, and researchers are working to develop observational tests that could distinguish between the different models of the early universe, including the standard Big Bang, the cyclic universe, and the bounce scenario. One of the most exciting areas of research in cosmology is the search for direct evidence of quantum gravitational effects in the early universe. While these effects are expected to be extremely small, they could leave subtle imprints on the cosmic microwave background (CMB), the afterglow of the Big Bang that we observe today. The CMB is a snapshot of the universe as it appeared about 380,000 years after the Big Bang, when the first atoms formed and the universe became transparent to light. By studying the tiny fluctuations in temperature and polarization in the CMB, scientists can gain insights into the conditions that existed in the very early universe, including the effects of quantum gravity and inflation. In recent years, cosmologists have made significant progress in mapping the CMB in unprecedented detail, using instruments like the Planck satellite and ground-based observatories such as the Atacama Cosmology Telescope. These observations have provided strong support for the inflationary model of the early universe, as well as hints of new physics that could be related to quantum gravity. For example, some models predict that the quantum nature of spacetime could lead to tiny, non-random patterns in the distribution of galaxies and galaxy clusters, which could be detectable in future surveys of the large-scale structure of the universe. Another potential source of information about the Big Bang comes from the study of primordial black holes, which are thought to have formed in the early universe, shortly after the Big Bang. Unlike the black holes that formed from the collapse of massive stars, primordial black holes could have been created by the extreme density fluctuations during the first moments of the universe's expansion. These black holes could range in size from tiny, subatomic scale objects to massive black holes with the mass of entire galaxies. Some theories suggest that primordial black holes could account for a portion of dark matter, the mysterious substance that makes up about 25% of the universe's total mass energy content. If primordial black holes exist, they could offer a unique window into the conditions of the early universe and provide clues about the physics of the Big Bang. Several experiments, including the Laser Interferometer Gravitational Wave Observatory, LIGO, and the European Space Agency's LISA mission, are searching for evidence of primordial black holes through their gravitational wave signals. Gravitational waves are ripples in spacetime caused by the acceleration of massive objects, such as merging black holes or neutron stars. The detection of gravitational waves from primordial black holes would provide a direct probe of the early universe and could help test theories of quantum gravity and inflation. In addition to black holes, the study of neutrinos, ghostly particles that interact very weakly with matter, could shed light on the Big Bang. Neutrinos were produced in vast quantities during the first few seconds of the universe's existence, and they continue to stream through space today as relics of the Big Bang. These primordial neutrinos, sometimes called the cosmic neutrino background, are much harder to detect than the CMB, but they carry valuable information about the earliest moments of the universe. Several experiments, such as the upcoming Ptolemy experiment, aim to detect these primordial neutrinos and use them to study the conditions of the early universe. As we push the boundaries of our understanding of the Big Bang, we are likely to encounter new challenges and surprises that will reshape our view of the universe. The study of the Big Bang is not just about understanding the past. It is also about exploring the fundamental laws of nature that govern the universe at all times and scales. Whether through the discovery of new particles, the detection of primordial gravitational waves, or the unraveling of the mysteries of dark matter and dark energy, the quest to understand the Big Bang promises to lead us to new frontiers in physics and cosmology. The study of dark matter and dark energy represents one of the greatest frontiers in cosmology, and is deeply connected to the Big Bang and the evolution of the universe. These two components, dark matter and dark energy, make up approximately 95% of the universe, yet their true nature remains elusive. While the Big Bang theory explains the creation of normal matter and energy, it does not fully account for these mysterious forces, leaving many unanswered questions about the structure and fate of the universe. Dark matter is thought to be a form of matter that does not emit, absorb, or reflect light, making it invisible to traditional telescopes. However, its gravitational effects can be observed, particularly in the rotation curves of galaxies and the large-scale structure of the universe. Without dark matter, galaxies would not have enough mass to hold themselves together. They would fly apart due to their rotational speeds. The leading theory suggests that dark matter consists of yet undiscovered particles, such as WIMPs, weakly interacting massive particles, but so far, direct detection of dark matter has proven difficult. In the context of the Big Bang, dark matter would have formed very early, potentially within the first second of the universe's existence. Its presence would have influenced the distribution of matter in the universe, guiding the formation of galaxies and galaxy clusters. Studying the role of dark matter in the early universe helps cosmologists refine models of structure formation and test different theories about the nature of dark matter. One of the most promising methods for detecting dark matter is through its gravitational effects on the cosmic microwave background, CMB. Precision measurements of the CMB can reveal subtle imprints left by dark matter during the formation of the first structures in the universe. Dark energy, on the other hand, is even more mysterious than dark matter. Discovered in the late 1990s through observations of distant supernovae, dark energy is the name given to the unknown force driving the accelerated expansion of the universe. According to the Big Bang theory, the universe has been expanding since its creation, but the discovery of dark energy revealed that this expansion is not slowing down, as was once thought, but speeding up. This acceleration has profound implications for the future of the universe, suggesting that it could continue expanding forever, eventually reaching a state of heat death, where all matter is so spread out that no structures can form. The nature of dark energy is one of the biggest unsolved mysteries in cosmology. Some theories suggest that dark energy is a property of space itself, known as the cosmological constant, which was originally proposed by Einstein in his equations of general relativity. Others propose that dark energy could be a dynamic field that changes over time, known as quintessence. Understanding dark energy is crucial not only for explaining the current expansion of the universe but also for determining its ultimate fate. Theories about the end of the universe, whether it will collapse in a big crunch, tear apart in a big rip, or fade into a cold, empty void, are all tied to the nature of dark energy. In addition to dark matter and dark energy, the study of black holes has also provided important insights into the Big Bang and the evolution of the universe. Black holes are regions of space where gravity is so strong that not even light can escape. They are formed from the collapse of massive stars, but there is growing evidence that supermassive black holes, with masses millions or billions of times that of the Sun, exist at the centers of most galaxies, including our own Milky Way. These supermassive black holes may have played a key role in shaping the structure of the early universe, influencing the formation of galaxies and galaxy clusters. One of the most intriguing connections between black holes and the Big Bang comes from the idea that the early universe may have been filled with primordial black holes, which formed in the chaotic conditions shortly after the Big Bang. These primordial black holes would be much smaller than those formed by stellar collapse, and they could have profound implications for our understanding of dark matter and the early universe. Some theories suggest that primordial black holes could account for a significant portion of dark matter, offering a possible solution to one of the biggest puzzles in cosmology. Another important area of research involves the study of gravitational waves, which are ripples in spacetime caused by the acceleration of massive objects. The detection of gravitational waves by LIGO in 2015 opened up a new window for studying the universe, allowing scientists to observe events such as the mergers of black holes and neutron stars. Gravitational waves provide a direct way to probe the conditions of the early universe, including the Big Bang itself. Some theories suggest that the Big Bang could have produced a primordial gravitational wave background, similar to the cosmic microwave background, which could carry information about the first moments of the universe's existence. Detecting these primordial gravitational waves would offer a new way to test theories of inflation, quantum gravity, and the origins of the universe. The study of gravitational waves also raises the possibility of testing the holographic principle, a speculative idea that suggests the universe could be a hologram, with all the information about three-dimensional space encoded on a two-dimensional surface. This idea comes from the study of black holes, which appear to store information about the matter that falls into them on their event horizons, the boundary beyond which nothing can escape. Some theorists believe that this principle could apply to the universe as a whole, with the Big Bang representing the moment when the information encoded on a two-dimensional surface gave rise to the three-dimensional universe we experience. The holographic principle is closely related to the study of quantum gravity, particularly in the context of string theory, which proposes that the fundamental constituents of the universe are not point-like particles, but tiny, vibrating strings. String theory offers a possible way to reconcile quantum mechanics with general relativity, providing a framework for understanding the extreme conditions of the early universe and the Big Bang. In string theory, the Big Bang could represent the moment when the universe transitioned from a higher dimensional state, such as a brane, into the four-dimensional spacetime we observe today. The idea that the universe could have originated from a higher dimensional state is also explored in the ekpyrotic universe model, which suggests that the Big Bang was not a singularity, but rather the result of a collision between higher dimensional branes in a larger, multidimensional space. This model offers an alternative to the traditional Big Bang scenario, in which the universe begins from a single point and expands outward. In the ekpyrotic model, the collision of branes could have triggered the expansion of the universe, with the energy from the collision giving rise to the matter and radiation we observe today. This model also raises the possibility that the universe could undergo a series of cycles, with each Big Bang representing the beginning of a new cycle of expansion and contraction. While the ekpyrotic model is still speculative, it highlights how modern cosmology is increasingly looking beyond the traditional Big Bang scenario to explore more complex and multidimensional models of the universe. These models challenge our understanding of space, time, and the nature of reality itself, suggesting that the Big Bang may not have been the absolute beginning of everything, but rather a transition from one phase of existence to another. As we continue to study the Big Bang and the mysteries of the early universe, we are likely to encounter new questions and paradoxes that will push the boundaries of our understanding. The quest to understand the origins of the universe is not just about explaining the past. It is also about exploring the fundamental laws of nature and the ultimate structure of reality. Whether through the discovery of new particles, the detection of primordial gravitational waves, or the unraveling of the mysteries of dark matter and dark energy, the study of the Big Bang promises to lead us to new frontiers in physics and cosmology. The mysteries of the Big Bang and the origins of the universe also touch upon philosophical questions that have intrigued humanity for centuries. The inquiry into why the universe exists at all, what preceded the Big Bang, and whether there is a purpose behind its evolution leads to profound discussions about existence itself. Such questions evoke metaphysical speculation that intersects with scientific investigation, challenging the boundaries between science and philosophy. One of the most intriguing questions related to the Big Bang is the concept of nothingness. If the Big Bang marks the beginning of the universe, what existed before it? Theories vary widely. Some suggest that time itself began with the Big Bang, making the question of what was there before nonsensical. Others speculate about a multiverse, where our universe is just one of many, potentially giving rise to various Big Bang events in a broader context. The idea of a multiverse raises further questions about the nature of reality and existence, as it suggests that our universe might be just one of countless others, each with different physical laws and constants. Additionally, the Big Bang poses intriguing questions about the fine-tuning of the universe. Observations reveal that the universe's fundamental constants, such as the gravitational constant, the speed of light, and the mass of elementary particles, are remarkably fine-tuned to allow for the existence of life. This fine-tuning has led some to propose the anthropic principle, which suggests that the universe must be compatible with conscious life because we are here to observe it. The anthropic principle has sparked debates about whether this fine-tuning is the result of random chance, a selection bias, where we can only exist in a universe that allows for our existence, or if it suggests deeper principles underlying the cosmos. One possible explanation for this fine-tuning is the idea that if there are many universes, the multiverse, then it is not surprising that at least one of them would have the right conditions for life. This notion opens a Pandora's box of philosophical implications. If there are infinite universes with varying laws of physics, what does that say about our own universe and our place within it? Are we merely a random byproduct of a much larger cosmic lottery? Moreover, the exploration of the Big Bang touches upon concepts of causality and determinism. The events leading up to the Big Bang are shrouded in mystery, and traditional notions of cause and effect may not apply. Some physicists propose that quantum fluctuations in a primordial vacuum could have triggered the Big Bang, suggesting a fundamentally non-deterministic nature to the universe's origin. This view aligns with certain interpretations of quantum mechanics, where uncertainty and probability reign supreme. The interplay between quantum mechanics and general relativity in the context of the Big Bang challenges our understanding of the universe's origins and its underlying structure. As we probe deeper into the nature of the universe, we are also confronted with the limitations of our current understanding. While the Big Bang theory is supported by a wealth of observational evidence, such as the cosmic microwave background radiation and the abundance of light elements, it is essential to recognize that our models are continually refined and revised as new data emerges. The advancement of technology, including more powerful telescopes and detectors, allows us to observe distant cosmic events and gather new insights about the early universe. Furthermore, the rise of artificial intelligence and machine learning and data analysis opens new avenues for exploration. These technologies can sift through vast datasets to identify patterns and anomalies that human researchers might overlook, potentially leading to groundbreaking discoveries related to the Big Bang and beyond. As our understanding of the universe evolves, we must remain open to new ideas and be willing to question established paradigms. The scientific method thrives on skepticism and inquiry, leading to the continuous pursuit of knowledge and understanding. The intersection of cosmology with other scientific disciplines also provides exciting opportunities for collaboration. For instance, advancements in particle physics, particularly in facilities like the Large Hadron Collider, LHC, could help uncover the fundamental particles and forces that shaped the early universe. The study of high-energy physics can provide insights into the conditions that existed just moments after the Big Bang, offering clues about the fundamental building blocks of matter and energy. Similarly, astrophysics plays a crucial role in studying the aftermath of the Big Bang. Observing the formation and evolution of galaxies, stars, and planetary systems provides valuable information about the universe's history and its structure. The processes that govern stellar formation and evolution also reflect the conditions that emerged from the Big Bang. By understanding how stars and galaxies form and interact, we can piece together the story of the universe and our place within it. The expansion of our universe also has implications for the future. As galaxies move away from us due to the universe's expansion, we face a situation where distant galaxies may eventually become unreachable. This concept, known as the observable universe, suggests that as time progresses, we will lose sight of many galaxies, isolating our local group from the rest of the universe. The ultimate fate of the universe, whether it will continue expanding indefinitely or eventually collapse, is still a matter of scientific debate. The study of dark energy plays a critical role in determining this fate, as understanding its properties will shape our predictions about the long-term behavior of the cosmos. As we contemplate the mysteries of the universe, it becomes clear that the Big Bang is not merely an event in time but a catalyst for an ongoing quest for understanding. It represents humanity's drive to explore the cosmos, unravel the fundamental laws that govern existence, and grapple with the profound questions of existence, purpose, and reality. The journey of discovery has just begun, and with each new finding, we are reminded of how much we have yet to learn. The Big Bang continues to inspire generations of scientists and thinkers, driving innovations and advancements that push the boundaries of knowledge. The ongoing quest to understand the universe's origins, structure, and fate invites collaboration across disciplines, merging the fields of physics, astronomy, philosophy, and beyond. In this shared pursuit of knowledge, we honor the legacy of those who came before us and contribute to the ongoing dialogue about the universe's mysteries. As we look to the future, the promise of new technologies, theoretical advancements, and collaborative research holds the potential to revolutionize our understanding of the universe. The questions surrounding the Big Bang will continue to challenge our intellect and inspire our curiosity. In this infinite cosmos, the mysteries of existence beckon us to explore, discover, and reflect upon our place in the grand tapestry of the universe. The journey through space and time is not just an exploration of the cosmos. It is a reflection of humanity's enduring quest for meaning, knowledge, and connection with the universe around us. Each new revelation brings us closer to understanding our origins, our universe, and our place within the vast expanse of existence. The Big Bang is but a beginning that continues to unfold as we delve deeper into the fabric of reality. The pursuit of answers may be fraught with challenges and uncertainties, but it is through these inquiries that we discover not only the universe's secrets, but also the depth of our own understanding. The adventure of cosmology is far from over, and as we continue to probe the mysteries of the cosmos, we are reminded of the beauty and complexity of the universe we inhabit. As we press further into the implications of the Big Bang, it's essential to consider the role of human imagination and creativity in the pursuit of understanding. Theories and models that emerge from the scientific community are not merely dry mathematical equations or abstract ideas. They are woven into a rich tapestry of human thought, culture, and aspiration. The narrative of the universe's origins inspires artists, writers, and philosophers, inviting them to envision the cosmos in ways that provoke reflection on our existence. The representation of the Big Bang in the universe in art and literature often captures the awe and wonder that accompany such grand ideas. From the works of visionary artists to the imaginative realms crafted by authors of science fiction, the cosmos serves as a backdrop for explorations of human nature, existential dilemmas, and the quest for meaning. This cultural engagement with cosmic themes fosters a collective consciousness that transcends disciplinary boundaries and enriches our understanding of the universe. In the realm of science fiction, stories about the origins of the universe have allowed writers to explore complex themes such as time travel, alternate realities, and the consequences of humanity's actions on a cosmic scale. Iconic works like Arthur C. Clarke's 2001: A Space Odyssey and Isaac Asimov's Foundation series examine the relationship between humanity and the cosmos, framing our journey within the context of the universe's vast history. These narratives serve as a canvas for reflecting on the ethical implications of scientific progress, our responsibility to the universe, and the interconnectedness of all existence. Moreover, the Big Bang Theory compels us to contemplate our role as observers of the cosmos. The act of observation itself introduces philosophical considerations about the nature of reality. The principle of cosmic observation states that the universe is observable because it has a finite age, leading to the conclusion that the cosmos is both a participant and an observer in its own evolution. This observation leads us to ponder the nature of consciousness and the connection between the observer and the observed, a concept that bridges physics, philosophy, and psychology. As we reflect on the significance of the Big Bang, we must also acknowledge the potential implications for future generations. The pursuit of cosmic knowledge is an ongoing legacy, one that fosters curiosity and innovation. Educational initiatives aimed at inspiring the next generation of scientists, engineers, and thinkers are crucial for maintaining the momentum of discovery. Engaging young minds in the mysteries of the universe not only cultivates a sense of wonder but also emphasizes the importance of scientific literacy in navigating the complexities of the modern world. Furthermore, the interplay between scientific discovery and public engagement cannot be overstated. Efforts to communicate the intricacies of the Big Bang and the universe at large through accessible formats, such as documentaries, podcasts, and interactive exhibitions, serve to bridge the gap between the scientific community and the public. By demystifying complex concepts and making them relatable, we empower individuals to participate in the conversation about our place in the universe and the implications of scientific advancements. The significance of the Big Bang extends beyond the realms of physics and philosophy. It touches upon the very essence of what it means to be human. As we grapple with existential questions, the mysteries of the cosmos prompt introspection and exploration of our values, beliefs, and aspirations. The pursuit of knowledge becomes a shared journey, one that binds us together in our quest for understanding. In recent years, the rapid advancements in technology and our increasing ability to probe the universe have opened new avenues for exploration. From the discovery of gravitational waves, ripples in space-time caused by cosmic events like merging black holes, to the imaging of black holes themselves, the frontiers of science continue to expand. Each new discovery serves as a reminder of the complexity and interconnectedness of the cosmos, revealing a universe that is both beautiful and unfathomable. As we delve deeper into the mysteries of the Big Bang, we must also consider the ethical implications of our scientific endeavors. The exploration of the cosmos raises questions about humanity's responsibility to preserve the integrity of the universe. The potential consequences of technological advancements, such as space exploration and colonization, compel us to reflect on the impact of our actions on the delicate balance of the cosmic ecosystem. The narrative of the Big Bang is not merely a historical account of the universe's origins. It is a living story that continues to evolve as we gather new insights. The interplay between science, philosophy, art, and ethics enriches our understanding of the cosmos, reminding us that our pursuit of knowledge is intrinsically tied to our humanity. As we navigate the complexities of existence, we are called to approach the universe with humility, curiosity, and a sense of stewardship. In conclusion, the Big Bang represents a profound and transformative moment in the history of the universe. It is a reminder of the interconnectedness of all things and the dynamic nature of reality. The mystery surrounding its origins and implications continue to inspire generations of thinkers, pushing the boundaries of human understanding. As we stand at the precipice of discovery, we are reminded that the universe is not a distant, abstract concept. It is a part of us, and we are a part of it. The ongoing exploration of the Big Bang and the cosmos is a testament to the resilience of the human spirit and our insatiable curiosity. The questions that arise from this exploration, about existence, purpose, and the nature of reality, are as vital today as they were in ancient times. The quest for understanding will persist, driven by our desire to uncover the secrets of the universe and our place within it. With each new revelation, we are reminded that the cosmos is not just a backdrop for our existence. It is a participant in the grand story of creation, and we are all integral parts of that narrative. As we continue to explore the mysteries of the universe, we invite you to join us in this ongoing journey of discovery. The Big Bang is just the beginning, a gateway to understanding the cosmos and our connection to it. Together, let us embrace the unknown, seek answers to the profound questions that challenge our understanding, and celebrate the beauty and complexity of the universe we inhabit. As we venture further into the exploration of the Big Bang, it's important to reflect on how our understanding of this monumental event has evolved over time. The journey of comprehending the origins of the universe is not merely a scientific endeavor but a human story marked by curiosity, imagination, and the relentless pursuit of knowledge. The history of the Big Bang theory can be traced back to the early 20th century when revolutionary ideas began to challenge traditional notions of the universe. Prior to this, the prevailing belief was that the universe was static and unchanging, a concept that had been largely accepted since the days of Aristotle and Ptolemy. However, groundbreaking work by scientists such as Albert Einstein, Edwin Hubble, and Georges Lemaitre transformed our understanding of the cosmos and laid the groundwork for the Big Bang theory. Einstein's theory of general relativity, introduced in 1915, provided a new framework for understanding gravity and the dynamics of the universe. It suggested that massive objects, such as stars and galaxies, warp spacetime, causing other objects to follow curved paths. This revolutionary perspective opened the door to new ways of thinking about the universe's structure and behavior. In the 1920s, Edwin Hubble made a significant discovery. He observed that distant galaxies were moving away from us, and the farther away they were, the faster they were receding. This observation, known as Hubble's law, provided compelling evidence for the expanding universe model. Hubble's findings suggested that the universe was not static but dynamically evolving, which aligned perfectly with Lemaitre's earlier proposition that the universe began as a singular, infinitely dense point, a concept that would later be termed the Big Bang. Lemaitre, a Belgian priest and physicist, proposed that the universe originated from a primeval atom, which exploded and initiated the expansion of space and time. His ideas were initially met with skepticism, but as more observational evidence emerged, the Big Bang theory gained traction. The discovery of cosmic microwave background radiation, CMB, in 1965 by Arno Penzias and Robert Wilson provided critical support for the theory, confirming that the universe had a hot and dense beginning. The CMB is often referred to as the afterglow of the Big Bang, a remnant radiation that permeates the universe. It serves as a snapshot of the infant universe, revealing information about its temperature, density fluctuations, and overall structure. The study of the CMB has become a cornerstone of cosmology, offering insights into the early universe's conditions and the subsequent formation of large-scale structures. The ongoing investigation of the CMB has also prompted questions about the nature of dark matter and dark energy, two enigmatic components that comprise the majority of the universe's mass-energy content. Dark matter, which does not emit or interact with electromagnetic radiation, plays a critical role in shaping the cosmos and influencing galaxy formation. Meanwhile, dark energy, a mysterious force driving the accelerated expansion of the universe, raises profound questions about the fate of the cosmos. These investigations into the fundamental components of the universe have led to the development of advanced theoretical models, such as inflationary cosmology. Inflation theory posits that a rapid expansion occurred within the first fractions of a second after the Big Bang, smoothing out the universe's initial irregularities and leading to the uniform distribution of matter and energy observed today. This inflationary epoch provides a framework for understanding the cosmic microwave background and the large-scale structure of the universe. However, the mysteries surrounding the Big Bang extend beyond the observable phenomena. They encompass fundamental questions about the very nature of time and space. If the Big Bang represents the beginning of time, it challenges our understanding of causality. What does it mean for something to come from nothing? And how do we define existence in the absence of time? These inquiries have led to philosophical debates about the nature of reality, consciousness, and the limits of human understanding. The relationship between time and the Big Bang also raises intriguing possibilities for the concept of cyclic universes. Some cosmologists propose that the universe may undergo endless cycles of expansion and contraction, with each Big Bang followed by a big crunch. This notion challenges the traditional linear view of time and suggests that our universe may be part of an infinite cycle of creation and destruction. Such theories invite contemplation about the nature of time itself and how it shapes our understanding of existence. As we approach the mysteries of the Big Bang from multiple angles, scientific, philosophical, and even artistic, we begin to appreciate the intricate web of questions and ideas that arise. The cosmos serves as a reflection of humanity's desire to explore the unknown and find meaning within the vastness of existence. Each discovery, each question, brings us one step closer to unraveling the enigma of the universe and our place within it. The importance of interdisciplinary collaboration in the pursuit of understanding the Big Bang cannot be overstated. Scientists, philosophers, artists, and educators all contribute to a richer understanding of the cosmos. Engaging diverse perspectives fosters a holistic approach to the mysteries of the universe, allowing us to integrate knowledge from various fields and create a more comprehensive narrative of existence. Educational initiatives play a vital role in inspiring future generations to engage with the cosmos. By nurturing curiosity and promoting scientific literacy, we empower individuals to explore the mysteries of the universe. Outreach programs, public lectures, and interactive exhibits allow individuals of all ages to engage with cosmological concepts, fostering a sense of wonder and appreciation for the vastness of space. The study of the Big Bang also underscores the importance of fostering a sense of global community in our scientific endeavors. As we grapple with questions that transcend national borders and cultural divides, it becomes increasingly evident that collaboration is essential in our pursuit of knowledge. The cosmos invites us to work together, to share insights and discoveries, and to celebrate our shared humanity. In a world marked by challenges and uncertainties, the exploration of the universe's origins offers a unifying vision, a reminder that we are all part of a grand cosmic story. The Big Bang is not just a scientific event, it is a testament to the power of human curiosity and the relentless pursuit of understanding. It encourages us to ask questions, to seek answers, and to embrace the unknown. As we stand at the precipice of discovery, the mysteries of the Big Bang beckon us to explore further, to probe deeper, and to reflect on our existence. The journey of understanding is ongoing, and with each new revelation, we come closer to unlocking the secrets of the universe. The Big Bang represents both a beginning and an invitation, a call to adventure that transcends the boundaries of science and speaks to the essence of what it means to be human. The unfolding narrative of the universe continues to captivate our imagination and inspire our exploration. As we gaze into the cosmos, we are reminded of the beauty and complexity of existence. The Big Bang is just one chapter in the grand story of the universe, and the pages yet to be written hold the promise of new discoveries and insights. Together, let us embrace the journey of exploration, fueled by curiosity, wonder, and the unyielding desire to understand our place in the cosmos. The mysteries of the Big Bang will continue to inspire generations to come, guiding us in our quest for knowledge and illuminating the path toward a deeper understanding of the universe we inhabit. In this grand tapestry of existence, each thread represents a unique perspective, a shared experience, and a collective aspiration to uncover the mysteries that lie beyond the stars. As we continue to explore the cosmos, we invite you to join us in this ongoing adventure, a journey filled with questions, discoveries, and the infinite possibilities that await. As we delve deeper into the implications of the Big Bang and its significance, we must also recognize the transformative impact that modern technology has had on our understanding of the universe. The tools and instruments developed over the past few decades have revolutionized our ability to observe and study cosmic phenomena, leading to a more profound comprehension of the origins of the universe and the fundamental laws that govern it. One of the most significant advancements in astronomy has been the development of space telescopes, such as the Hubble Space Telescope and the more recent James Webb Space Telescope, JWST. These observatories have provided unprecedented views of the cosmos, allowing scientists to gather data on distant galaxies, stars, and even exoplanets. The ability to peer into the distant reaches of space has allowed researchers to observe the light from galaxies that formed shortly after the Big Bang, offering crucial insights into the conditions of the early universe. Hubble's observations of the cosmic expansion have helped refine our understanding of the rate at which the universe is expanding, leading to more precise measurements of the Hubble constant. However, the JWST takes this exploration a step further, using infrared technology to detect the faintest signals from the earliest stars and galaxies. By studying these primordial objects, scientists can gain a clearer picture of how the universe evolved over billions of years, from the initial moments of the Big Bang to the formation of complex structures like galaxies and galaxy clusters. Moreover, the advances in gravitational wave detection have opened a new window into the cosmos. The Laser Interferometer Gravitational Wave Observatory, LIGO, has made groundbreaking discoveries by detecting ripples in space-time caused by cosmic events such as the merging of black holes and neutron stars. These observations not only validate aspects of the Big Bang theory but also provide new avenues for understanding the dynamic processes that continue to shape the universe. The interdisciplinary approach to studying the Big Bang fosters collaboration between scientists, philosophers, and artists, further enriching our understanding of the universe. Physicists work alongside cosmologists, mathematicians, and even computer scientists to model and simulate the early universe's conditions, bridging theoretical concepts with empirical data. These collaborative efforts highlight the importance of diverse perspectives in unraveling the mysteries of the cosmos, as each discipline brings unique tools and insights to the table. Philosophers contribute to the discussion by examining the implications of our understanding of the universe's origins. Questions about the nature of reality, the concept of time, and the role of observers in the cosmos provoke profound philosophical inquiry. The relationship between science and philosophy becomes increasingly intertwined as we explore the limits of human understanding and grapple with existential questions that have persisted for centuries. In this vein, the Big Bang theory has sparked debates about the implications for metaphysics and theology. The idea that the universe had a beginning raises questions about the nature of existence itself. For some, the Big Bang serves as evidence of a creator or an intelligent force behind the cosmos, while others argue that it can be explained through natural processes without invoking supernatural explanations. This intersection of science and belief encourages dialogue about the nature of reality, the limits of human knowledge, and the potential for understanding the universe through both scientific inquiry and spiritual exploration. Art also plays a vital role in interpreting and communicating the complexities of the Big Bang and the cosmos. Artists often draw inspiration from scientific discoveries, translating abstract concepts into visual representations that resonate with the public. The universe's vastness and intricacies can be challenging to convey, but art has the power to evoke emotion and wonder, inviting viewers to engage with the mysteries of existence in new ways. The fusion of science and art is exemplified in various creative endeavors, from immersive planetarium shows that depict the cosmos to large-scale installations that invite viewers to contemplate their place within the universe. These artistic expressions serve as a bridge between scientific understanding and human experience, highlighting the interconnectedness of all things and fostering a sense of awe in the face of the cosmos. As we reflect on the significance of the Big Bang, it becomes evident that our journey of discovery is far from complete. The mysteries surrounding the universe's origins continue to captivate scientists and thinkers alike, prompting ongoing research and exploration. The questions that arise from this inquiry, about the nature of time, the fundamental forces of the universe, and the potential for life beyond Earth, remain at the forefront of scientific inquiry. The exploration of the Big Bang is not just an academic pursuit. It is a quest that resonates with our deepest human instincts. The desire to understand our origins and the universe we inhabit is a fundamental aspect of our humanity. It compels us to seek knowledge, to explore the unknown, and to grapple with the mysteries that define our existence. As we continue to navigate the complexities of the cosmos, it is essential to approach our inquiries with humility and an open mind. The universe is vast and intricate, and our understanding is but a small fragment of the greater whole. Each discovery adds to the tapestry of knowledge, inviting us to explore further and embrace the uncertainties that lie ahead. The Big Bang serves as both a beginning and a gateway, a reminder that the universe is a dynamic, ever-evolving entity that continues to unfold before us. Our journey of exploration is driven by curiosity and wonder, igniting a passion for discovery that transcends generations. As we gaze into the cosmos, we are reminded that we are not mere observers. We are participants in the grand narrative of existence. Our quest for understanding connects us to the past, present, and future, weaving a tapestry of knowledge that spans time and space. In conclusion, the Big Bang represents a profound moment in the history of the universe, a moment that shapes our understanding of reality and our place within it. It invites us to explore the mysteries of existence, to engage in dialogue across disciplines, and to embrace the awe-inspiring complexity of the cosmos. As we continue this journey together, we invite you to reflect on the questions that arise from our exploration of the Big Bang. What does it mean for us to exist within such a vast universe? How do our experiences shape our understanding of the cosmos? And what role do we play in the unfolding narrative of existence? The quest for knowledge is an adventure that connects us all, inspiring us to delve into the unknown and embrace the mysteries of the universe. Together, let us celebrate the beauty and wonder of the cosmos, fueled by curiosity, imagination, and the unyielding desire to uncover the secrets that lie beyond the stars. As we close this chapter on the Big Bang, we recognize that the story of the universe is ongoing. Each discovery, each question, and each moment of reflection adds to the richness of our understanding. The cosmos beckons us to explore further, inviting us to join in the collective journey of discovery that defines what it means to be human. The mysteries of the universe await us, and together, we embark on this extraordinary adventure, a journey filled with questions, discoveries, and the infinite possibilities that lie ahead. As we delve even deeper into the intricate tapestry of the universe and the implications of the Big Bang, we begin to realize that understanding our cosmic origins is not merely an intellectual exercise. It is a deeply human pursuit. This quest for knowledge is intertwined with our identity and sense of belonging in a vast, ever-expanding cosmos. The exploration of the Big Bang and its aftermath brings us face to face with profound questions that challenge our perception of existence itself. One of the most intriguing aspects of the Big Bang theory is the concept of cosmic inflation. Proposed in the early 1980s by physicist Alan Guth and others, Inflation posits that the universe underwent an exponential expansion within the first fraction of a second after the Big Bang. This expansion would have caused the universe to grow from subatomic scales to macroscopic sizes almost instantaneously. The implications of inflation are profound, as they help to explain several observed features of the universe, including its large-scale structure and uniformity. During this brief moment of inflation, quantum fluctuations in the fabric of space-time may have seeded the formation of galaxies and other large structures we observe today. This idea presents a fascinating connection between the microscopic quantum realm and the macroscopic structure of the universe, suggesting that the fundamental building blocks of reality may influence the grand cosmic scale. Understanding inflation not only deepens our knowledge of the Big Bang but also challenges our perceptions of time and space, suggesting that the very fabric of the universe is woven from the interplay of quantum mechanics and cosmic expansion. The evidence for the Big Bang and inflation has been gathered through various observations, most notably through the cosmic microwave background (CMB) radiation. This relic radiation, discovered in the 1960s, is a faint glow permeating the universe, a remnant of the hot, dense state of the early universe. The CMB carries invaluable information about the conditions that prevailed shortly after the Big Bang, providing a snapshot of the universe when it was just 380,000 years old. The uniformity of the CMB across the sky indicates that the universe was once in a hot, dense state, and tiny fluctuations observed in its temperature map correlate with the initial density variations that would later give rise to galaxies and cosmic structures. The study of the CMB has become a cornerstone of modern cosmology, allowing scientists to refine their models of the universe's evolution and gain insight into its age, composition, and overall dynamics. Yet, as we strive to understand the cosmos, we encounter enigmatic challenges that continue to perplex scientists. One of the most pressing questions is the nature of dark matter and dark energy. Observations reveal that ordinary matter, which makes up stars, planets, and galaxies, accounts for only a fraction of the universe's total mass energy content. The majority of the universe's mass appears to be composed of dark matter, an invisible substance that does not emit, absorb, or reflect light, making it undetectable by conventional means. Dark matter plays a crucial role in the formation and stability of cosmic structures. Its gravitational influence helps to explain the observed rotation curves of galaxies, which indicate that stars on the outer edges are moving at higher speeds than would be expected based solely on the visible matter present. The search for dark matter candidates has led scientists to propose various hypothetical particles, such as WIMPs, weakly interacting massive particles, and axions. Despite extensive experimental efforts, dark matter remains elusive, highlighting the limitations of our current understanding and the need for innovative approaches in both theoretical and experimental physics. In addition to dark matter, the phenomenon of dark energy poses another conundrum. Observations of distant supernovae and the large-scale structure of the universe suggest that the expansion of the universe is accelerating, driven by an unknown force referred to as dark energy. This mysterious entity constitutes approximately 68% of the universe's energy density, and remains one of the most significant unsolved mysteries in cosmology. Various theories have been proposed to explain dark energy, including the cosmological constant, a concept introduced by Albert Einstein, and modifications to our understanding of gravity. The implications of dark energy challenge our fundamental notions of space and time, prompting questions about the ultimate fate of the universe. Will the expansion continue indefinitely, leading to a cold, desolate future, or will the gravitational forces of matter eventually halt this expansion? Such questions underscore the profound impact of the Big Bang on our understanding of time, existence, and the ultimate destiny of the cosmos. The relationship between the Big Bang and the ongoing cosmic expansion invites contemplation of larger philosophical questions about the nature of time itself. Time, as we perceive it, is intimately tied to the unfolding of events in the universe. The Big Bang marks the beginning of time as we know it, leading us to consider the implications of time's directionality, commonly referred to as the arrow of time. The increase in entropy, as dictated by the second law of thermodynamics, suggests that time moves forward, driving the universe toward a state of greater disorder. Yet, the concept of time is more complex than a simple progression from past to future. Theories in physics, such as general relativity, suggest that time may be more malleable than we realize, influenced by gravitational fields and relative motion. These ideas prompt profound inquiries about the nature of reality. Is time an absolute framework within which events unfold, or is it a relative construct shaped by our experiences and observations? As we navigate the mysteries of the universe, we also confront questions about the existence of other life forms. The sheer scale of the cosmos and the vast number of galaxies, stars, and potentially habitable planets raise tantalizing possibilities for the emergence of life beyond Earth. The discovery of exoplanets in the habitable zone around their parent stars has intensified the search for extraterrestrial life, spurring missions to explore the icy moons of Jupiter and Saturn, such as Europa and Enceladus, which harbor subsurface oceans that may provide suitable environments for life. The potential for life elsewhere in the universe invites reflection on our own existence. What does it mean to be a conscious being in a universe that has evolved from the chaos of the Big Bang? Are we a rare occurrence or part of a vast network of intelligent life? The answers to these questions remain elusive, yet they underscore the importance of understanding the conditions that led to our own emergence. As we contemplate the implications of the Big Bang and our place in the universe, we also recognize the significance of storytelling in our exploration of these cosmic mysteries. The narratives we construct around our origins shape our understanding of existence and influence how we engage with the world. The myths, legends, and scientific theories that emerge from our quest for knowledge reflect our deepest desires to comprehend the universe and our role within it. In the grand tapestry of existence, we find ourselves not just as observers but as participants in a cosmic story that transcends time and space. Each discovery adds a new thread to this narrative, weaving together the threads of science, philosophy, and art. As we explore the mysteries of the cosmos, we are reminded that the pursuit of knowledge is a journey marked by curiosity, wonder, and a profound connection to the universe. In closing, the Big Bang serves as both a scientific foundation and a philosophical catalyst for our understanding of existence. It invites us to ponder our origins, confront the unknown, and embrace the interconnectedness of all things. The mysteries of the universe beckon us to explore further, to ask questions, and to seek answers that illuminate the path of our cosmic journey. As we continue to delve into the enigmas of the universe, we are reminded that the story of the cosmos is far from complete. The Big Bang and its implications serve as a testament to the richness of inquiry and discovery, reminding us of the infinite possibilities that lie ahead. Each moment of reflection, each question posed, and each discovery made contributes to the ever-evolving narrative of existence, a narrative that invites us to engage with the mysteries of the universe and celebrate the beauty of our shared journey through time and space. The cosmos is a boundless frontier, filled with mysteries waiting to be uncovered. Our exploration of the Big Bang is but one chapter in the grand saga of the universe, a story that will continue to unfold as we seek to understand our place within the cosmos. The adventure of discovery is one that unites us all, a journey driven by curiosity, wonder, and an unwavering desire to uncover the secrets of existence. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.